We talked about functions the last few days, what made something a function and stuff like that. And today what we're going to look at are some different properties of functions. I mean, there's properties where it talked about, kind of the intercepts, stuff like that. But today we're going to talk about kind of a classification of functions. You can classify them as even or odd, similar to numbers. The only difference is pretty much all your whole numbers are even or odd, right? But some functions are neither. They're kind of special cases when they are even and when they are odd. We're going to look at those graphically and then with their equation. And then we're going to start talking about increasing, decreasing, or constant, and max and min, both local and absolute. We're just looking at graphs for those last three. If you go into calculus, you learn how to find those without the graph as well. Though there is a way to do it algebraically, it just takes a little time. Time consuming. Alrighty, so first things first, you got graphs or functions. Let's say functions. Functions can either be even or odd, or they can be neither. A function f is even if for every x in its domain, the number negative x is also in the domain. So what that's saying is basically if you have the point x comma y, you also have negative x comma y. Which you may think sounds familiar. Anybody remember where that's from? No? Well, if you remember, that means that it is symmetric with respect to the y-axis. Remember, if it's symmetric with respect to the y-axis, if you have a point here, that's x comma y, you're also going to have the opposite point here, negative x comma y. So what that means is that if a function is even, it needs to be symmetric with respect to the y-axis. Any questions on that? Okay. A function f is odd if for every number x in its domain, the number negative x is also in its domain, and f of negative x is equal to negative f of x. What that is saying is if you have x comma y, you also need to have negative x comma negative y. That will make it odd. Does that seem familiar? Order, yeah, good. So it's symmetric with respect, blah, blah, blah. I'm going to shorthand them a little bit. Do the origin. So if you see a function that is symmetric with respect to the origin, that means it's an odd function. Which one's missing? We did the y-axis and the origin, the x-axis, right? But if something was symmetric to the x-axis, it wouldn't be a function. It would fail the vertical line. So that's why that is not one that we're talking about. And so that note's repeated here. Function is even if and only if its graph is symmetric with respect to the y-axis. A function is odd if and only if its graph is symmetric with respect to the origin. If and only if means that that relationship goes both ways. So it's even, that means it's symmetric with respect to the y-axis. If it's symmetric with respect to the y-axis, that means it's even. And you can see, I wrote it like here as well. But I think y'all get the point. I have my note 3 times. Any questions on that? So let's look at some examples. Got these 3 graphs. We want to figure out if they're even odd or neither. Or put neither in there. So graph A. What do you think that is? Even, odd, or neither? Even. It's even. It's symmetric with respect to the y-axis, right? If you floated it here, this curve will match this curve. And so if it's symmetric with respect to the y-axis, it is an even function. Any questions on that? What about graph B? That's symmetric with respect to the y-axis. What about the origin? Does this match this? Does this match this? No, so this is going to be neither. This is just a function. It's not even, it's not odd. I think they have to say neither even nor odd or something like that. That's how they word it in that homework. Questions on B. And C, what do you have? Y-axis, does this match this? No. Origin, does this match this? Does this match this? Yep. So this is an odd function. Any questions on that? No? All right. Oh, I did not. Okay, good. Didn't you? All right, so determining if a function is even or odd is pretty simple with the graph. You just determine if it's symmetric with respect to the y-axis, symmetric with respect to the origin, and there you go. You just got to remember which one relates to which one. To figure out if it's even or odd from the equation is a little bit more difficult. What we're going to have to use is those relationships we talked about at the beginning, where if x comma y is in it and it's even, then it has to have negative x comma y. And if x comma y is a point or is an ordered pair from the function, then negative x and negative y need to be as well for it to be odd. We're going to use that. And so to do that, what we're going to do is check this. If f of x, sorry, if f of negative x is equal to f of x, that means that it's an even function. And it may seem kind of confusing, like how do we know that? Well, remember we said that for it to be even, if x comma y is there, that means that negative x comma y needs to be there, right? F of x is just y. So we're saying that the two y values are going to be equal if it's x or negative x. That's all we're saying. Just like we have written here. That's where that comes from. And if you ever get confused, like I do, because I have a hard time memorizing stuff, just remember that if it's even, xy and negative xy need to be there. So f of negative x has to equal f of x. And we learned how to do this yesterday, I feel like. And this we already know how to do, it's just the function. To see if it's odd, we're going to check to see if f of negative x is equal to negative f of x. That comes from the fact that if it's odd and has x comma y, then it also needs to have negative x comma negative y. So when you plug in a negative x, you get the negation of that y value. And that's all you have to check. And if you remember, this is kind of similar to what we did for those, when we were talking about symmetry. Remember, we plugged in a negative y or a negative x. It's kind of the same thing we're doing. It's just we're dealing with a function instead. All right, so let's try some out. So A, should have spaced these out. I guess I got lazy. We got f of x is equal to x squared minus 5. We want to check to see if it's even or odd. So let's do the even check first. I like to do the even check first because if you look at what you're doing, for even, you just have to find f of negative x, right? And so if we find that it's even, then we're good. But if it's not even, then we already have that one part for the odd. We just got to find that part. So they kind of, I don't know, it just makes the path easier for me, my mind. So to check if it's even, let's do green for even. We're going to replace the x with negative x and see if that equals our original function. That's what we want to know. So we already know what f of x is x squared minus 5. Let's figure out what f of negative x is. Just like we did yesterday, we're going to plug in a negative x for the x. So we're going to have negative x squared minus 5. And can we evaluate the negative x squared? Give me a positive x squared. So this is going to equal x squared minus 5. Does that match my original function? It does. That means this function is even. Any questions on that? No? You're good. Do I need to check if it's odd? You're saying no. Why? Why not?
Oh yeah, because it could be both.
Can it be both?
No, it can only be both.
Let's think about it. So this isn't this graph, but let's say I'm gonna draw a graph of one that is even, right? That's an even function. It's symmetric with respect to the y-axis, right? If it was also odd, it would also need to be symmetric with respect to the what? The origin. So that means it would have to be this here, this here. What's the problem there? It's not a function. So a function can only be even or odd or neither. It can't be even and odd. So once you determine that a function is even, you don't have to go any further and check to see if it's odd. That is the reason being, because remember, I talked about it a little bit when we're doing symmetry. If it's symmetric with respect to the y-axis, in order for it to be symmetric with respect to the origin, it also needs to be symmetric with respect to the x-axis. But it can be symmetric with respect to the origin and not the other two. So that is basically what you're looking for. For even functions, it's just symmetric with respect to the y-axis. For odd functions, it's just symmetric with respect to the origin. If it was multiple symmetries, then it would be not a function. Any questions on that? Cool. That's my eraser. Yep. All right, let's try B. What do y'all think B is going to be, even or odd? It's x to the third minus 1. You think it's going to be odd? Let's see. So I'm going to test even first anyways. You could do odd first if you wanted to, but I really just feel like it makes it easier to do even first. So we're going to do g of negative x. That's going to be, well, let's write out what we're doing. I don't want to go too fast yet. So we're trying to see if g of negative x is equal to g of x, right? That's what we're trying to see. And so we're going to do g of negative x is going to be negative x to the third minus 1. negative x to the third can evaluate to just be negative x to the third. But does that match my original function? No, there's a negative hanging out right there, so this is not even. Not even. So let's look at odd. So for odd, we're trying to see if f of negative x, which we are, we're doing g, huh? G of negative x is equal to negative g of x. We already know what g of negative x is. That is what we found right here. So what we're going to look for is negative g of x. But remember, it's just like multiplying your function by negative 1. That's going to be negative x to the third plus 1. Does that match that? No. So that means this function is going to be neither. Either, even, or odd. C, h of x is equal to 5x to the third minus x. What do y'all think for this one? Even or odd? Odd. Why are you saying odd? Yeah, this is understood to be a 1. So those are both odd numbers. I would say this one's probably odd. Let's test it out. Yeah. So we'll do even first. Well, we could do odd first if you want, but I always like doing even first. I'm trying to see if h of negative x is equal to h of x. So h of negative x is what? It's going to be f. No, sorry, 5 times negative x to the third minus a negative x. And so that is going to be negative 5x to the third plus x, which does not match my original function. So it's not even. So let's look at the odd test and try to see if negative h of x is equal to h of negative x. So we already know what h of negative x is. We just need to figure out what is negative h of x. So that's multiplying my whole function by negative 1. I get negative 5x to the third plus x. And lo and behold, boom, and boom, those match up. So this function is an odd function. Any questions on that? What do y'all think this one's going to be, even or odd? It is x to the 1. Let's see what happens. Let's do even. We're trying to see if f of negative x is equal to f of x. F of negative x is going to equal the absolute value of negative x. What can we change that to? Can we evaluate that any? Is it going to be, oh, I don't need to write that again. Are you saying it's just going to be like x?
Yeah.
Not necessarily, but you're close. It's going to be x, but the absolute value is still going to be there. But you still need to apply the absolute value. Because what if x was a negative number, right? If it was like negative 5, we negate it again, it's going to be positive 5. Take the absolute value of that, it's going to be 5. So you can get rid of the negative inside the absolute value, but you need to retain the absolute value. And so does that match our function? Yes, it does. So even though this was x to the 1, it's the absolute value function. This one is an even function. And I feel like we talked about the absolute value function at some point, maybe. I mean, I've been in another class. It looks basically like this. And so you can see that is, in fact, even. Symmetric with respect to the y-axis. Any questions on that? All right. We already talked about this next thing. I kind of brought it up before. Can a function be both even and odd? So let's talk about increasing, decreasing, and constant. So there's actually some debate going on about some of the stuff here. I'll talk about it, but I'll talk about how I like to think about it, and maybe that will convince you to my way of doing it. But we're going to talk about where is the function increasing, where is it decreasing, and where is it constant. Now, remember that for our x-axis, we were increasing from left to right. So when we're talking about increasing, we're going to be traversing the x-axis from left to right. And so the easiest way for me to describe this is think about you're in like a little roller coaster, right? And you're going to follow the curve of this graph from left to right. From here to here, you are what? Are you going up or are you going down?
No.
You're going down. So you're decreasing here. Once you hit this point, you start going up. And so you're increasing from here to here, but you continue to increase. Even though the way that it's increasing changes, you're still increasing. So you will be increasing from here to here. Any questions on that? That's what tends to get people is when it changes up a little bit. As long as it keeps increasing, we're still increasing. From the 0 to 3, what are we doing? It's not changing, so it's constant. And then from 3 to 6, we are decreasing, right? There's a technical way of defining this, and I think I have it written. Yeah, it's below. It's below. Oh, no, that might be the next page. It is. There's a technical way to define it, and we'll talk about that later. But that's basically all it means to increase, decrease, and constant. We're trying to give the biggest intervals on which it's increasing. So if we broke this one up, it would be decreasing right here. It would be increasing right here. It would be constant right here. And then it would be decreasing. Any questions on that? We'll come back to this graph afterwards. Okay, so how do we describe where is this function increasing, decreasing, or constant? What do you think? If I want to know where is this, let's do the easiest one. Where is this graph constant? How would you tell me that?
Would you use the bar because it's a code sentence?
Oh, that's okay. So you're right. We're going to use, what do we call that when you write it like that? You remember? It's interval notation, right? And so what kind of interval are we going to talk about? Are we going to talk about y interval or x interval? X. So we're saying anytime someone asks you where something is happening on a two-dimensional graph, they want x values. So it's from this x value to this x value. So what's this x value where it started being constant? Anybody know? Is what? 0. So we start being constant at 0. Where do we stop being constant? 3. So you want to write the largest interval you can. So don't say from 0 to 1. Because technically it is constant from 0 to 1, but it's also constant from 1 to 3. So you want to have the largest interval you can. Any questions on that? All right, so here's the kind of controversy that we currently have going on. So do you think we want to include the 0 and the 3 by putting brackets, or do we not want to include the 0 and the 3 by putting parentheses? Why do you say include? Because it's a closed circle. So the closed circle just means that that is part of the function, right? It means that that value is defined when x is 0, y is 4, right? If it was a closed 0, it means that 0 wouldn't be in the domain of the function. So there's different thoughts on it, and the homework will actually allow you to put it in either way, as far as I know, last I checked. And we've been in contact with the publisher about it, but the way that I think about it is we're trying to say, where is the graph constant, but it's not really changing at that singular point of 0, right? It's like saying, what is your speed? Or you take a picture of a car driving on the road and you say, looking at the photograph, what was the speed of that car? You don't know what it's doing at a singular point. It's just a point. If you only look at where x is 0, can you tell that it's constant there? Not really. Can you tell that it's increasing or decreasing? No, because it's just a singular point. So my opinion on it is that we don't include those end values. You just put a parenthesis. Now, the issue is that when you get to calculus, you can figure out what is it doing at those values. And so I think that's why the book started including them. And so you can do either one. I would recommend doing the parentheses just because that's how it used to be. I don't know when that changed, but the book and the homework's allowing either or. Any questions on that? And I think it's a little bit more obvious when we start talking about, like, where is it increasing? So what is the interval in which it's increasing? Starts at -4, stops at 0. So that's going to be from -4 to 0. And so, like I was saying, like at that point, is it increasing? It's just a point. I don't know. At that point, is it increasing? I don't know. So we'll just put parentheses on it. And then the last one, decreasing. What are we going to put for decreasing? -6 to -4. And then we're going to union it. Yep, exactly. And we're going to put what? 3 to 6. Now you can also, it is accepted. Can I move this? No, it's all one thing. To write it as, I'll write it over here. Or maybe I won't. There we go. -6 to -4, comma, 3 to 6. But I think they're going to tell you to use a union in the homework, if I recall correctly. Because it's like you're listing an interval, this interval, and this interval. Or you can use the union, which means it's this interval or this interval, which is what I like better. I feel like I've seen this before. Any questions on that? All right. What are we? Oh, technical definitions next. Yep. So here's the technical definition for increasing and decreasing. A function f is increasing on an open interval I if for any choice of x of 1 and x of 2 in I with x of 1 less than x of 2, we have that their y values, f of x of 1 is less than f of x of 2. This picture right here shows it. If you select some x value and some other x value that's greater than it, the y value of this one should be less than the y value of that. That's all it's saying. Just a really complex way of saying it. Any questions on that? If it's decreasing on an open interval I, and for any choice of x values, x1, x2 in that interval, where x1 is less than x2, then their y values, f of x of 1 is going to be greater than f of x of 2. So the same thing, we're selecting x1 and x2 such that x1 is less than x2, then its y value should be greater than this y value because it should be decreasing as we go along. And it should be that way for any x values you choose. And it's constant if we're on an open interval I, that for all choices of x and I, the values of f of x are equal. So no matter what x you choose, the y values are the same. Which makes sense. And we already talked about that. Any questions on that? All right. So let's talk about local maxima and local minima. Maxima and minima is just a plural term for maximum and minimum. Because for a local one, you can have multiples. So let f be a function defined on some interval I. So there's some interval I that's defined on of x values. A function f has a local local maximum at c if there is an open interval in I containing c, so that for all x in this open interval, the y values around the y value at c is less than or equal to it. We call f of c a local maximum value of f. So all it's saying is that there's a peak, there's a hilltop on your function. You can have multiple of them. It could come back up, and this would also be a local maximum. Now, remember some of the way of writing this usually gets confusing to people. For this one here, we would say that we have a local max at x equals c, and the local max is whatever f of c is. So the y value is the max. Where is the max at? That's what the x value is. I always just think about like a mountain. Where's the peak of the, if you ask me where the peak of the mountain is, I'm going to give you a location, longitude and latitude. If you want me to know what's the peak of the mountain, I'm going to give you an elevation. How high is it? And the same thing for minimums. It's going to be the bottom of the valley, the bottom of the canyon, however you want to think about it. Where's the minimum happening? At x equals c. What is the minimum? It's going to be the y value. Any questions on that? Yeah, cool. All right, so if we're looking at this right here, and let's say, well, if I want to find the local minimum, let's say local minimum. How many local minima do we have? How many bottoms of a valley do we have in this graph? Two. Got one right here, one right here. I meant to actually circle them. There we go. Where are these happening at? So x is -1, so we'll have at -1 and 3. So we have local minima at x is equal to -1 and x is equal to 3. And what value does it have? What's the y value at -1? It's 1. And what's the y value at 3? 0. There you go. Any questions on that? Talk about local maxima. And they're called Nissan maxima. So we have a local maxima at x equals what? Oh, we got the top of the hill here, or the top of the mountain here. It's at x equals 1, and it has a value of what? Y equals 2. There you go. It does not matter that my graph keeps going, right? We're just looking in that locality. It's the max on the surrounding area. These are mins on the surrounding area. That's what makes it a local min, local max. Like if you live in a small town and the popular person in that town maybe not popular nationwide, but popular in that. The local celebrity. Local maxima, local minimum. Any questions on that? So we can talk about absolute maxima and absolute minimum, or absolute maximum and absolute minimum, because we shouldn't have multiples. So if we want to know where in their graph is it absolutely the bottom, absolutely the top, that is what absolute maximum and absolute minimum are. Usually they'll give us a closed interval or some interval to choose from, so that we're not worried about the whole graph. But we'll look at all the different things that can come up. So you're basically looking for the same thing. Local min, we were looking for a low point, but for absolute min, we're looking for the lowest point, the absolute lowest point on the graph. Local max, we're looking for a high point. Absolute maximum, we're looking for the highest point, the absolute highest point. Okay. So if we're looking at a graph like this, where is my absolute minimum is going to be? We got A, U, B, and B. What's the absolute? Did I say minimum or maximum? Minimum. Minimum. Where's my lowest point? B, right? Now, we need to look at the endpoints and this point and make sure that this one's lower. It is. So the absolute min would be at x equals b. And it would have a value of b, f of b. That's hard to say, f of b. What about my absolute max? What's the highest point? U. That's at x equals u. That would be my absolute max point. That's my highest point on my graph. All right, so let's look at some other ones. Let's look at A. And let's do absolute min and absolute max. So what's the highest point? Well, what's the lowest point on that first graph? It's 0. Notice it's happening at the end point, right? We have a local min here at 4, but it's not lower than this point. That's my lowest point there. So this is going to be, let's just write it as an order pair, 0, 1. So it's happening at x is equal to 0 as the value of 1. What about my absolute max? What's the highest point? Close. 3, right? At 5 is 5, 5, right? But at 3, it's 6. So my absolute max is going to be at 3 with a value of 6. Any questions on that? Let's see the next. What about B? What's my absolute min? Be careful. Like, I mean, you may have a hard time seeing it, but is it defined at 3? It is the lowest point. It's the dip, right? But it's an open circle, so it's not defined at 3. And so absolute min, we're gonna have none. There's no absolute min there. What about absolute max? Oh, you got 1, 2 up here. You got 5, 3 right here. So this one's gonna win here. So it's gonna be 5, 3. Because it is defined, right? Those are endpoints. Yeah, they're full dots.
So why wouldn't the 1, 2, why would they be considered as like the lowest point?
But it is at the lowest point. Comes down here, right?
Oh, okay.
The problem is, so if we tried to pick the lowest point here, it's impossible to do because it keeps getting closer and closer to where y is 1 as x gets closer and closer to 3, which is kind of an abstract thing. It's something that we learn if you go on through math. Probably like calculus, you probably start learning it there. But we can't isolate what's the lowest point there. It's just going to keep getting closer and closer to 1, but never actually be 1. And so that's the problem that we have. And let's look at C. Any questions on B? Any other questions? Let's look at C. So what do we have for C? What's going to be the absolute min? Yeah, so the actual value of the absolute min is going to be 1, right? Because the y value is 1. But it's going to happen twice. So you have 1, 1. I wouldn't union them because they're order pairs, right? They're not intervals. So it's just 1, 1, 2, 1. It happens twice, but the lowest value is 1. And what would be the max? 5, 4. Yep. Any questions on C? All right, let's look at D. Absolute, what was the first one? Absolute min. What's the lowest point? 0, 0. Yep. What about the absolute max? Can you isolate a value that's the highest value? It's just going to keep going, right? No, we don't know. What else? E. Absolute min. Yeah, it just keeps going down, right? This is what we call a vertical asymptote. This is just going to go down to negative infinity here. So we have none. What about absolute min? Oh, sorry, absolute max. Yeah, sorry. Yeah, same. We got the same situation we had before, right? It's not defined there, so we'd have none there too. That'd be it. So you have a local max, right? If I can grab the thing, there we go. You got a local max there, but this goes past it and it's not defined there, so we can't do it. So that's all the different ones that can happen. That you'll see. Do I have that note on here? Any questions on those? Now notice some of these were open interval or a half open, half closed. That means that it's, the endpoints aren't defined or the open circles. But there is a note. Whoa. Let me zoom out. There's a shortcut to zoom out, but it never works. All right. If f is a continuous function, which means there's no gaps or anything when you're drawing it, whose domain is a closed interval, so the endpoints are defined, then f has an absolute maximum and an absolute minimum on that closed interval. So if it is a closed interval, it has to have a max or a min. So if, in simple terms, if the function f is an unbroken smooth line from x equal to a to x equals to b, then the function of f has an absolute maximum and absolute min on AB. If we look back at the ones we were just looking at, this one is defined on a closed interval. We had absolute max and absolute min. This one is a closed interval, but it's not defined at 3. So that's why we don't have that minimum. This one's defined on a closed interval. Notice we had both. Boom. This one is defined, but it's not a closed interval. It just keeps going. That's why we end up with the none here. And then this one is not a closed interval, and it's not continuous. So, none. So those are all the different situations that can arise